In this recording, we're going to talk about binomial distributions. Thank you for joining me. Now, binomial distributions are actually a very big topic, and it can get pretty complicated. But for us, all we're going to really do is just start to get familiar with the concept of binomial distributions, that they exist. We're not going to learn any of the really complex formulas that go along with binomial distributions. So what we're going to do is we're just going to practice seeing patterns in some very simple binomial distributions, ones with just a couple of trials instead of, we could do this with 4 or 5 or 6 trials or selections, which would get really complex fast, but we're only going to do a couple each time. All right, so just want to reassure you that we're not going really deep, and one of the cautions I should give you is that if you were to look up binomial distributions using Google search, you would come to some really complicated stuff. Don't do that. Just watch this recording, maybe watch it a few times, and then do the practice problems in the lessons, hopefully with repeated exposures. So you hear this a few times, you'll start to feel comfortable with just how much you're supposed to know, and then you don't have to worry about the stuff you're not supposed to know. Okay, we're going to list the requirements for a binomial distribution. That's the first thing we're going to do. One of the things we're going to practice is, does this have everything it needs to have to be a binomial distribution? Then we're going to create a binomial distribution using a tree chart, and then we'll represent what we find in a table or graph. And then we'll interpret data from a binomial distribution. Okay, so binomial distribution, a variable has binomial distribution if, here's 3 requirements. There are a fixed number of trials. Okay, so the classic one is flipping a coin. You say, I'm going to flip a coin 5 times. That would be a binomial distribution. If you say, I'm going to flip the coin until I get tired, that would not be, because you didn't set a fixed number of trials. The outcome of each trial is either a success or a failure. Now, the word binomial implies that there's 2 things. Bi means 2, and that's what it is. That each time you do the experiment or the trial or whatever it is, you're either going to succeed. Okay, you'll have one type of event that you'll say, if this happens, this is a success, and then anything else that happens would not be a success. So it's either yes, you succeeded, you got what you wanted, or you didn't. So on that coin flipping thing, you say heads is success, then tails would be failure. Okay, then the third thing that we're looking for is that the probabilities of each trial are the same. And later on, we're going to see that one of the key phrases that are going to show up for this thing is with replacement. So I'll go ahead and give you that example now. Instead of flipping a coin, which when you flip a coin, the chances of heads and chances of tails is 50% every single time. So that never changes. But let's give the example of, you have a bag and you have a bunch of marbles in the bag. And some are, let's say some are red and some are white. Right now with this example, the probability of drawing a red is 2 out of 5. Okay, but if I took one of the marbles out, and let's say it was a red one, then the next time the probability would not be the same. If I took one of the red ones out, so now I have 4 marbles left and only one of them is red, the probability is 1 out of 4. And so the probability of success is different on the second draw than it is the first draw. And the reason for that is because I didn't put my marble that I drew out the first time back in the bag. So in order for it to be a binomial distribution, I have to put the marble back in the bag. Every time I draw a marble out, look at it, record it, success or failure, and then put it back in the bag. Okay, that's one of the main examples of where you're going to see is the probabilities. Do the probabilities remain the same for each trial, or are they different? That's one example of how that might happen. Okay. Let's take a look. I'm going to look at one that's a bad example of the one that's not a probability that's not a binomial distribution. It's this one. Over the next 4 days, x, and we always define the variable as our success. X is the what would be defined as a success. X is the number of days it will rain. Okay, so x is the number of successes, which is defined as days that it rains. All right, so we have 3 requirements for this to be a binomial distribution. Requirement number 1, set number of trials. Do we have a set number of trials? Yes, 4 days. We said in advance we're going to look over the next 4 days. That's that. Okay, so far so good. Number 2, binomial. That just means that there's 2 choices. We could say success or failure, and that's true here. We have the thing that we're measuring is days that it rained. So if it rains, that's a success. And no rain equals failure. There's no third option here. I think one of the examples we saw in the lesson is it said if you're driving around and you're recording whether each stoplight is red or green or yellow when you get to it. And that would not be binomial because you're recording 3 different things. It's not a success or failure. It's 3 different things instead of 2 things. Okay, so this is still good. We're still happy with this. This still could be a binomial distribution until we get to number 3. And that is the probabilities stay the same each time. Now, this is a little bit tricky, and that's why this is the trick question. What is the chance that it's going to rain today? What's the chance it's going to rain tomorrow? What's the chance it's going to rain the next day? It turns out that those the answers to those questions are different each time. So the chance of rain is not the same every day. The probability of rain is not the same every day. So this would not be a good binomial distribution because probabilities are different. Okay, hopefully that helps you kind of see the process you need to go through to decide if a situation is going to result in a binomial distribution or not, asking those 3 questions. So, well, let's do it again. We're going to do this one more time. I have 3 different scenarios here, and in each case, we're going to ask, is this a binomial distribution or not? So the first one, I flip a coin and record heads until I get 50. Okay, is this a binomial distribution? Well, question number 1, is there a set number of trials? And the answer is no. I didn't say I'm going to flip a coin 50 times. I said I'm going to keep flipping it until I get 50 heads. So no, that is not a set number of trials. So this is not a binomial. We don't even have to check anything else. This is the coin flipping one. So generally coin flipping ones are binomial, but because I didn't specify the number of trials, that's not binomial. Okay, number 2, the second one. You draw a marble out of a bag, record if it is red, green, or blue. You do this 5 times, replacing the marble each time. Okay, so question number 1, set number of trials. The answer, yes, 5 times. We're going to do this 5 times. So check check number 1. That's good. Question number 2. Each draw is either a success or a failure. This is that example where we're not looking for one thing and either we get it or we don't. We're actually recording 3 different things. And so this is not binomial, it's trinomial, I guess you could say. And that's not going to fit into our binomial distribution. So this is not a binomial distribution because question number 2, the answer was no. Okay, last example. Oh, and we did replace the marble each time, so remember that was one of our keywords for that third question, are the probabilities the same. So the probabilities will be the same, but still not binomial. Okay, you eat 10 M&Ms out of a bag containing only the red and the green. Record how many are red, or you could say X equals red. And so red would be a success, and then green would be failure. So that's binomial. You're going to do this 10 times. You're eating 10 M&Ms. So the question number 1, set number of trials, yes. Binomial, question number 2, yes, it's binomial. Success is red, failure is green. Question number 3, are the probabilities the same? And this is that situation where as I'm taking the M&Ms out, I'm not putting them back, I'm eating them. And so every time I eat another M&M, there's fewer left in the bag, and the probability of success has changed from what it was before. So this, again, is not a binomial distribution. So so far we're only giving you examples by negative examples, because it fails on the last question. All right, well, let's get into some other questions that are real binomial distributions. And you're going to have to watch closely here because I don't have a whole lot of examples. So we're going to try to explain these ones really thoroughly. A bag with 3 red and 7 blue, I think it was supposed to be marbles. Draw 1 at a time with replacement and record how many are red. So X equals red is the vocabulary that we're using. X equals red, that's the success. If you draw a blue, that would be a failure. So this is binomial. It's with replacement, so the probabilities are the same each time. And oops, I didn't specify how many trials we're going to do, but we're going to say 2 times. And we're going to create a binomial distribution. And when you see how we do this, you'll see why I said 2 times and not 3 or 4, because it can get complicated really fast. Okay, so the way we're going to do this is with a tree diagram. And so it's like we're standing here and we have a choice. And we're going to draw 2 lines to represent the 2 choices that we have. Choice number 1, we could draw a red marble. And choice number 2, we could draw a blue marble. Okay, now we're not actually going to choose with our eyes open. We're going to randomly choose. But those are the 2 outcomes that could happen. Now each outcome has its own probability. And you remember how to set up probabilities. Probability of red in each case is going to be 3 out of the total number of marbles, which is 10. 3 plus 7 is 10. And the probability for blue is going to be 7 out of 10. So the probability of drawing the red is 3 out of 10. The probability of drawing the blue is 7 out of 10. Now once you've made that choice, you're either standing here with a red marble, which you're going to put back in the bag, or you're standing here with a blue marble, which you're going to put back in the bag. In either case, you have another draw. You have to draw 2 times, so we have 2 more choices. The second choices are the same as the first. We could either draw a red or a blue. The probabilities are the same, 3 out of 10 or 7 out of 10. And we have to draw those choices from both branches of our tree from our first choice. And now these branches represent paths you can go on and destinations you can end up at. And I hope you can see that there are 4 destinations. And I'm going to use a highlighter to try to highlight the paths. So we could have gone on this path, choose a red, and then choose another red, so that we end up with having chosen 2 reds, a red and a red. And what's the probability of doing that? In the lesson, it makes a point of saying that the probability of doing 2 things, here's what it says: the probability of x and the probability of y is equal to the probability of x times the probability of y. Because the probability of drawing a red the first time and drawing a red the second time is the probability of each multiplied together. So 3/10 times 3/10, which is 9/100, or 9%. Okay. Let's do the highlighter again, and this time we'll highlight a second path we could have gone on. We could have gone on the red path again, but then the second draw taken the blue path. That highlighter is not very nice. And if we had gone on that path, we would have ended up with a red and a blue. And the probability of doing that is the probability of drawing a red, 3/10, 30%, times the probability of drawing a blue, 7/10, which is 3 times 7, 21, 10 times 10, 100, 21 out of 100, or 21%. Okay. Next path we could have gone on. Let's pick a different color. We'll do orange. We could have gone on the blue path. Right? We've gone on the red path twice, first time, and then the red path. So we could have gone that path there. If we had, we would have ended up with a blue and then a red. Now that's the exact same probabilities. This time it's 7/10 times 3/10, but it's the same answer. 7/10 times 3/10 is the same as 3/10 times 7/10. It's 21/100, or 21%. So notice those probabilities are the same, and the actual results are the same too. If I draw a red marble first and a blue one second, I've only drawn 1 red marble. If I draw a blue marble first and then a red marble, I've still only drawn 1 red marble. I've only had 1 success. Okay, so we're going to put those together in just a minute. And then finally, the last path we could have gone on was that the blue and then a blue again. So we ended up drawing 2 blues, which is 2 failures. We didn't ever draw a red. And the chances of that would be 7/10 times 7/10. 7 times 7 is 49. 10 times 10 is 100. 49 hundredths, or 49%. So by far the most likely outcome was never drawing any reds in this situation, because there's so few red marbles and so many blue marbles. You have almost a 50% chance of not ever drawing a red. But now let's put this into a chart, and there's 2 ways to draw this. We could do a chart. I'm going to do a chart with X standing for my numbers of successes, and P standing for the probability. Now there's actually only 3 choices. The numbers of successes in 2 draws could have been 2. I could have gotten 2 red marbles, 2 successes. Could be 1. Could have gotten 1 red marble out of 2 choices. Or it could be 0. 0 red marbles out of 2 choices. Those are the only choices. And the probability of drawing 2 red marbles we saw is 9%. The probability of drawing 0 red marbles is 49%. What's the probability of drawing 1 marble? Well, this is the other thing that they talked about in the lesson. I think they wrote it like this. I did this wrong the first time. The probability of x or y is equal to the probability of x plus the probability of y. So what's the probability of drawing either a red and then a blue, so only one red marble, or a blue and then a red, which also results in 1 red marble? The probabilities are the same, 21%. The probability of doing one or the other of those 2 choices is these 2 probabilities added together. So we add 21 plus 21% to get a total of 42%. So the probability of drawing 1 marble out of this situation in 2 draws is 42%. Probability of drawing no red marbles is 49%, and 1 red marble would be 2 red marbles would be 9%. Notice that those 3% add up. This is a probability distribution. They add up to 100%, so that matches. And then we could have done this as a bar graph. So I could have said 0, 1, 2, 49%, 42%, and 9%, and had this as a bar graph. So that, just be aware that you might see data represented as a bar graph, you might see it represented as a chart, or you might have to calculate it yourself from a situation like this. Let me just point out that if I had decided to do 3 draws, then I would have had to draw 8 more V's, 8 more branches, 8 more sets of branches, which is 16 branches, right? 2 more here, 2 more here, 2 more here, 2 more here, and so then I would have 4 times 2. Let's see, that would have been 4 more pairs. That's 8 results. So there would be 8 destinations instead of 4 destinations, and that would just make our job a lot harder in coming up with our chart. So recognize that the more draws we have, the kind of more complicated this gets, and so we're not going to do that. In the problems we're going to see are going to be fairly simple. Which brings us to this last one. This is our second trick question. This really is a trick question. Which probability matches the probability histogram? Assume that there were 2 trials. Okay, so we did the same thing we just did with 2 trials. X equals 2, where X represents the number of successes. So instead of saying, here's the number of marbles and calculate the probabilities, this is saying, here's the probabilities, and here it is in a histogram for 0 successes, 1 success, and 2 successes. What were the probabilities to begin with? What was the probability of success to begin with? Okay, so let me draw a tree diagram and see if we can kind of work this backwards. So we have our tree diagram where we have success and failure, and then we don't know what the probabilities are. Okay, so I'm just going to put a circle there to represent that we have to fill that in. We don't know what it is. Success, failure. Again, I don't know what the probabilities that I'm multiplying are, but we do it again. Success, failure, 2 more the probabilities are all the same. And then when I multiply together, when I get two successes, that ends up having these two probabilities multiplied together. And according to the chart, the probability of two successes is, just kind of taking this line over, is 0.6. So it's almost halfway between 0.6 and 0.7, just under halfway. So I'm going to say 0.64 instead of 0.65. So the probability is 0.64 or 64%. Okay? So the question is then, what probability multiplied by itself equals 0.64 or 64%? You think about that. Well, I go down and look at the two failures. If I had two failures, then I would multiply my failure probabilities together. The two, that'd be the same probability, multiply together. And when I do that, I get this number down here. This one's harder to see. It's 0.0, I think that's 0.04. 0.04 or 4%. So there's a 4% chance of failing twice. Well, what percent times itself equals 0.04? And hopefully you figured this out by now. 64 is 8 times 8, so it's 8%. It's not 8%, it's 80%. It's 0.8. 0.8 times 0.8 is 0.64. And the other half of that, right, if 80% is success, then it'd be 20% failure. 0.2, and 0.2 times 0.2 is 0.04. So that matches up. And then we can see what our other probabilities would be. 0.8 times 0.2 would be 16%, and 16%, which added together is 32%. And that's what we have right here. This, if you follow this line across, it's about 32%. So the probability of one success and one failure is 32%. Probability of two is 64%. Probability of 0 successes is about 4%. And the only way you would get those probabilities is if the probability of success is 80%, 0.8, and the probability of failure is 2%, 20%, or 0.2. Okay, so the question says, what is the probability of success? And the answer is, probability of success is 80% or 0.8. That was complicated. I gave you more details than you needed. Obviously, all you had to know is that a success on two draws would be success times success equals 0.64. What number times itself equals 0.64? That's 0.8. You can do the square root of 0.64 on your calculator. And so the probability of 0.8 gives us the 64% for both things happening twice. Okay, so once we saw that, we were done. We knew what the answer was. We didn't have to figure out the probability of the failure or fill in the rest of the chart, but just so you get used to this, I went ahead and showed you that. Whew, that was a lot. Thank you very much for watching. I hope this was helpful. Again, remember, the more you see it, the more you try it on the practice problems in the lessons, the more sure of yourself you'll become, and the quiz will be a piece of cake. Thanks for watching, and have a great day.